Welcome back to Integral Calculus. In this video, I want to introduce you to L'Hopital's rule, which is a powerful tool for dealing with limits in indeterminate form. This rule is named after the French mathematician L'Hopital, and before we get into the crunch of it, I did want to... oh boy. There we go. I did want to at least quickly mention that the spelling of his name has two common versions. In the French language, you include the accent on the O. In most other languages, putting accents on letters is not the norm, and so the rewriting of L'Hopital's name in English language very often is written in this way with an S in there that does not exist in the original French. Either way, it's pronounced L'Hopital, and they're both considered acceptable. All right, with those conventions out of the way, let's dive into the actual rule. All right, this is a theorem. I'm not going to do a very good job of proving this, but I'm going to kind of give you the basic flavor of why this should work. And in fact, I'm going to start by looking at the 0 over 0 indeterminate form. L'Hopital's rule does work no matter what indeterminate form it is, whether that's 0 over 0, infinity over infinity, or one of the others that you may not have seen prior to this video. They all will work. It's just that the 0 over 0 is the one that's easy to prove. But if we have functions so that that is the case, then it turns out that the limit as x approaches c of f of x over g of x is equal to the limit as x approaches c of f prime of x over g prime of x. You can take the derivative of the numerator and take the derivative of the denominator and still have the limits have the same value when you're working with the ratio. This is strange because it's not really an operation on the equation, or the operation is the L'Hopital operation. And so for that reason, in order to try to better explain what happened in this step, it's become a standard convention that we annotate the equal sign and put L'H on it to indicate I used L'Hopital's rule to get this next step. I'm going to do my best to always do that when I'm writing out notes. I strongly encourage you to get in that habit in this course, but it's not a universal requirement, so if you're looking at resources elsewhere, you may or may not see it. But to prove this result, I'm going to make another assumption that may or may not be a good one. Specifically, that the limit as x approaches c of f of x is equal to f of c is equal to 0. And the limit as x approaches c of g of x is equal to g of c is equal to 0. Right, that is the easiest way to end up with a 0 over 0 indeterminate form. It's not the only way, but it makes sense. And if we accept that that's what happened, it makes the proof manageable. Because now I can write the derivative of f of x, f prime of x, well, specifically at the point C. Well, The limit definition, this is not the one that you're probably most familiar with, but it is one that you have almost certainly seen at some point. F of x minus f of c all over x minus c. If you plug in x equals c plus delta x, then this turns into the more familiar version of the limit definition, but it does still work. We can do the same thing for g of x. Right? G prime of c is equal to the limit as x approaches c of g of x minus g of c all over x minus c. Now, the reason that I made these additional assumptions is because I want to clean up at this step. Because we are looking at this specific case, and I'm sorry, there should still be limits there. There we go. We are still looking at the limit as x approaches c, but f of c is 0 and g of c is 0. Now, if I want to take the limit as x approaches c of f prime of x over g prime of x, that's going to be f of c over, f prime of c over g prime of c, which is the limit as x approaches c of f of x over x minus c over g of x over x minus c. And the over x minus c's cancel each other out, leaving me with the limit as x approaches c of f of x over g of x. I can go through other special cases. I can look at, well, what if the limit as x approaches c of f of x and g of x are not actually 0, but it happens that when you take the ratio, you still end up with this 0 over 0. Well, that makes it messier, but we can go through that proof. What if instead of a 0 over 0, we have an infinity over infinity indeterminate form? Well, that makes it messier, but you can still go through that proof. Actually, that one's not too bad. Assign 1 over f of x goes to infinity, and 1 over g of x goes to infinity, which means that f of x and g of x both go to 0. And then you can basically use the same proof from there. All right. I don't want to get too bogged down in the details, but I did want to show you that it does actually fall out pretty quickly in some algebra when you play around with things. I was definitely not as precise and all-encompassing as general as I could have been with the proof, but it still gives us the flavor of, yes, this is a thing, and yes, it follows the rules that we're familiar with. The important question, though, why do we care? Well, the rules we have for dealing with indeterminate forms, specifically with algebraic expressions. If we had polynomials, we knew what to do. But what if we don't? What if we want to take the limit as x goes to 0 of sine x over x? Well, if you try evaluating, sine of 0 is 0. And of course, when x is 0, so we have 0 over 0, which is an indeterminate form. Because of that, and because we have transcendental functions, not just polynomials, I want to try using L'Hopital's rule. We will still have the limit as x approaches 0, but we'll have the derivative of sine of x, which is cosine of x, and we'll have the derivative of x, which is 1. Well, now we can just directly evaluate. Cosine of 0 is 1. 1 divided by 1 is 1. So the limit as x goes to 0 of sine x over x is equal to 1. You may have seen a more complicated way of showing this particular limit. Sine x over x is a common application of the squeeze theorem. But now that we have the power of derivatives in our back pockets, we can make our lives a lot easier and not have to worry about that squeeze theorem. All right, continuing onward. How about the limit as x approaches infinity of e to the x over 2x plus 9? Well, something positive like e raised to the infinity power is going to go to infinity, and then 2x plus 9 is also definitely going to go to infinity. So here we have an infinity over infinity indeterminate form instead of a 0 over 0, but L'Hopital's rule will still hold. So we want to set this equal by L'Hopital to the limit as x approaches infinity. The derivative of e to the x is e to the x. The derivative of 2x plus 9 is 2. Unfortunately, in this case, we still end up with an infinite limit. The limit does not exist. That's not a fault of L'Hopital's rule. That's just nature of limits. Combining infinity and 0 in other ways can produce other indeterminate forms. So for example, if I want to take the limit as x approaches 0 of x times the natural log of x. Well, as x goes to 0, x goes to 0. But as x goes to 0, the natural log of x goes to negative infinity. And so we have 0 times infinity, and we can kind of think of that, right? We saw that infinity commonly happens when you have something divided by 0. So yeah, if you kind of squint and tilt your head, you can think of this as a 0 over 0 indeterminate form. But technically it is something different. It is 0 times infinity indeterminate form. But if we have an indeterminate form, we can use L'Hopital's rule. But how? We don't have a fraction. How do we make this look like a fraction so that we can use L'Hopital's rule? A common option is to rewrite this as natural log of x over 1 over x. And you can test at this point, this is going to give you the infinity over infinity indeterminate form, which is definitely still an indeterminate form, but now we have it as a fraction, and because we have it as a fraction, we can use L'Hopital's rule. Right, the derivative of natural log of x is 1 over x. I forgot to write my limit in. We're still taking the limit as x goes to 0. We'll have 1 over x. The derivative of 1 over x is negative 1 over x squared. And if you simplify this, again, I guess first of all, notice here that we have still an infinity over infinity indeterminate form, so we have to do more work. We don't need L'Hopital's rule anymore. We now need the basic rules of algebra and dealing with indeterminate limits. Right? So multiply both top and bottom by x squared, or divide by x to the negative second, however you want to think about it. And we're going to end up with x over negative 1, which we can just evaluate. It's going to be 0 over negative 1, which is just 0. This case is a very important one, but it's also, I hate going through this one. It's very tedious, but we can manage it. It is important. It probably is the indeterminate form that comes up most often. If I try evaluating this, well, 1 over x squared when x goes to 0 is going to be 1 over 0, which goes to infinity. 1 over tangent of x, tangent of 0 is 0, 1 over 0 goes to infinity. So we have infinity minus infinity, which is an indeterminate form. And if we have an indeterminate form, we're going to have to hope that we can do something useful with it. If we had it written as a single fraction, we could use L'Hopital's rule, but we don't have that. But we can probably get there. If I find common denominator, I can write this as tangent of x minus x squared over x squared tangent of x. You can check at this point, as x goes to 0, we'll have tangent of 0, which is 0. We'll have x squared, which is 0. We have 0 over 0, which is the easier indeterminate form to deal with. There is no nice way to reduce this fraction. So to L'Hopital's rule we turn. Whenever you have indeterminate forms and you have transcendental functions, things that are not just polynomials and combinations of polynomials, we turn to L'Hopital's rule. All right, the numerator in this case is not that bad. The derivative of tangent is secant squared. The derivative of x squared is 2x. In the denominator, we are going to have to use the product rule. Derivative of first times the second is going to be 2x tangent x. And first times derivative of the second is going to be x squared secant squared x. Right, so that was annoying, but we got through it. If we try to evaluate at this point, we get our disappointment. As x goes to 0, secant of x is 1, but x itself is 0. This limit doesn't actually exist. This is going to be an infinite limit. Is it going to be positive infinity or negative infinity, or maybe both coming from different directions? I don't know. I don't particularly care. That's a little bit beyond what I want to get into in this video, but it is going to be infinite, and so that's the end of our story. Right? I like thinking about this one. Right? When you have infinity minus infinity, right? Infinity can come in different sizes. We don't know which of those infinities is the bigger infinity. So if they're the same size infinity, this might come out at 0. If one infinity is bigger than the other, it's going to come out as infinity or negative infinity, or it might even come out as a finite value. It might come out as like 7. Weird things can be disguised in infinity, because if you take infinity and you add 1, you get infinity. And if you take infinity and multiply by infinity, you get infinity. There are so many things weird that happen with infinity. Infinity is weirder than you think it is. So we always have to tread carefully. All right. One more example. Let's take the limit as x approaches infinity of x raised to the 1 over x power. This is probably the strangest indeterminate form. If we try evaluating this, we're going to get infinity raised to the 1 over infinity, which is 0 power. That is an indeterminate form. And because it is an indeterminate form, we need to try to figure out how to make this work. And how to make this work is one of those things that you look at and you say, no, it can't work that way. That doesn't make sense. I don't believe it. And then you do it and it works. And so you start trusting it, but it still doesn't make sense. You don't believe it. And if you feel that way at the end of this video, you're in the right place, because I've been teaching this for several years at the point I'm recording this video, and I still don't believe it, but I understand it and I know how it works, and I'm able to show you how it works, and that's the part that matters. Let's let y equal x to the 1 over x power. Then the natural log of y is equal to the natural log of x times 1 over x. Natural log is a one-to-one function, so we can just take a log of both sides of the equation. But then we can use the properties of logarithms to write this as 1 over x times the natural log of x, or natural log of x over x. All of a sudden, I turned this into a fraction. And now that I've turned it into a fraction, we're trying to figure out the limit as x approaches infinity of y. But I'm going to not just figure that out, I'm going to figure out e raised to the natural log of the limit as x approaches infinity of y, and I'm going to claim that I can bring that natural log inside of the limit. So I have e raised to the limit as x approaches infinity. Natural log of y is the same thing as natural log of x over x. And this limit is infinity over infinity indeterminate form. I can reduce it using L'Hopital's rule. We have e raised to the limit as x approaches infinity. Well, the derivative of natural log of y is 1 over x. The derivative of x is just 1. So we have e to the limit as x approaches infinity of 1 over x. That limit is 0, and anything raised to the 0 power is 1. With what I have just shown you, there is one last indeterminate form that I'm running low on time for. It is the 0 raised to the 0 power indeterminate form. And I would like you to explore that. In the simplest way I can manage to find for you to explore that, take the limit as x approaches 0 of x raised to the x power. Right? Based on what I just showed you for the infinity to the 0 indeterminate form, see what you can do with this. All right, and I'll see you in the next video.